Welcome back. I've been out and about traveling to different cities and countries, so I haven't been able to make a lot of videos, but this one today is going to be more specific about how to work on box structures or stiffened structures at the preliminary design stage. So if you go to Google, or if you're familiar with things, if you're designing a box structure or a big structure, it could be for machine base, could be for some kind of support tooling or something like that. Maybe it's welded together, maybe it's fabricated together with rivets or bolts or something like that. Doesn't really matter. But if you look at, let's see, go to the right page here. If you go to search Google for instance of ship hull construction, here they are welding a lot of ribs and stringers here to a ship hull. This method could be used for preliminary design of something like that, or even for starting to look at a stiffened structure more like an isogrid, which is either 3D printed or machined flat and then rolled into shape, or even possibly machined this way, depending on how severe the design is. But it's for doing the conceptual design of more complicated structures without going through all the details. You may have limited resources and time. You may not have FEM available when you're doing the initial design or concept, or someone else is going to be doing the work and they need to know specific geometry. And geometry can always change, and that's the beauty of doing preliminary conceptual design like this. I also made a blog article about this, pretty short. I will show that right here, and I will provide a link to this in the description of the video. So let's talk about the very basic concept here. Let's talk about like a rectangular stiffened box structure, and I want to understand the stresses and the deformations as a box structure. As you see, it's a stiffened box structure. It's got some ribs on it. I don't know necessarily during the preliminary design how tall this is going to be. I don't know how many ribs I'm going to have. But I do know, maybe for the design requirements, how stiff this needs to be. If I load this up with a lot of pressure or a lot of load, it's going to distort. The first thing that comes to mind is, well, maybe this is going to be, sorry, I lost my view there. But maybe this is going to be size, or maybe there's going to be a lot of interfering systems or cutouts for maybe piping or plumbing or something like that. You don't really know. But there's going to be a time where you're going to have to worry about deformations. You're going to have this initial perfectly shaped structure, and you're going to load it up, and it's going to go into a bent shape because you're loading it in one way or another. And you want to know how far that's going to bend, what the stresses are, things like that. So how do you go through this basic concept? Now, one way to do this is you can take this more 3D model. It's got some thickness to it, and you can go and make I don't know if it's easy to see on the screen, but you can make a basic shell model out of it, meaning you put a FEM model in and you just give it some plates and say there's this many. Pretty easy to build. It takes some finesse. You can't do it easily in things like SolidWorks simulation, but you could do it very easily parametrically in something like Abacus or possibly even ANSYS. I'm not sure. I am not as familiar with ANSYS as I am with Abacus, but you could do that. And you could change the height of the ribs. You can change the number of ribs maybe and do it that way. But that still takes time. That means you need a FEM license. That means if something major changes, you have to redesign this. Or, I don't know. there's a lot of things that can happen during a conceptual phase, and you don't necessarily want to be going through and remaking this FEM every time. So what do you do? Well, a lot of these structures, there's a simple way where you can approximate this using, and by this I mean this box rib structure. You can come up with an equivalent moment of inertia. And I go over that more in my blog article. But you take, unfortunately I don't have a very more refined drawing right now, but you can take this more complicated structure that is a, it's got upper and lower plates, maybe just lower plate, maybe just upper plate, but it's got some stiffening structure with it. And you figure out the moment of inertia of an equivalent plate. And this is used all the time in a composites industry. You take the moment of inertia of the face sheets and you say, well, I'm not worried about the stiffness of what's between the face sheets. So you throw that out and say, I've got an equivalent plate. Great. Now you take that thickness of your equivalent plate and then you throw it into a hand calculation from Rourke's or some other handbook that gives you the right boundary conditions you need. The difficulty of this method is that if it's not a simple shape, if it's not a simple circular plate, or if it's not a rectangular plate or something like that that's in Rourke's or some other handbook, you can't really do this. But if you come up with this equivalent plate and you have access to FEM and you have a more complicated geometry and you don't know what the stiffeners could be, you could make a simple shell model of just one plate, give it that equivalent thickness that represents the moment of inertia of the stiffeners and the face sheets, but it's only that single shell, and give it the geometry it's going to have, so it would resemble more the overall shape of a structure like this, but you don't have to model all the stiffeners. So you just model the rough conical shape here, and you take advantage of and you basically mock these stiffeners with an equivalent thickness of the plate in the FEM program. This is done all the time, and it's been done for decades, but a lot of the younger engineers don't do this, or a lot of the guys that just haven't grown up with hand calculations don't do this sort of thing. So this is a great method. I'm not going to go into details in this video. That's to come later, but it's just something to think about. It's a way of simplifying the initial design when you don't know the number of stiffeners, you don't know the exact shape of things. You can play around a lot with geometry very quickly. This is something that you want to be able to accomplish very quickly at the beginning stages of design. You don't want to model all of these ribs and all of these stiffeners and stringers. You want to basically come up with a shape without having to worry about computer time and modeling complexity, because you may not have the resources available to do all these things. Okay, now, next part of this. So we talked about you have to worry about, okay, well, I take this plate and I bend it. Well, the truth is this bending shape, which you're kind of used to seeing, that's approximately the shape. I just kind of fudged it in there. But what you don't necessarily think about is the effects of shear. So let me turn off these other shapes here. Shear on one of these box structures, especially for something that's short in span, is incredibly important, because bending is only part of it. And when you do the bending calculations, usually the ribs that are here in this structure, they give you zero or almost zero bending stiffness, because those face sheets are what matters. But what does matter is the shearing deflection, or what those ribs do account for is just shearing deflection. When you have a lot of ribs, you get a lot of shear stiffness, and this shear deflection will get lower. And because this is very short span, this is a pretty substantial effect. In some cases, I've seen this be as large as the bending deflection. So when you get and you combine, so you had your original shape, you have your bending deflection, you can just sum up these bent and shear deflection. So look at that. You got the shear deflection, you have this bending deflection, boom. Now you've got a shear and bending deflection, which together are more severe than your bending deflection alone. And the handbooks like Rourke's will only give you that bending deflection. They talk a little bit about some shear corrections and things like that, and it's worth looking into, but it's a little bit complicated to understand. But just know that a lot of the reason when you're looking at the initial design of things that your hand calcs do not match up with your FEM is because you're dealing with something that is short span and you're not accounting for shearing deflections. Very important for a complicated structure like this, especially when you're approximating results by hand. But you can do it, and it works. I've gotten really good results by doing this equivalent plate formulation with Rourke's. Works really well, incredibly good. And then from these results, by using Rourke's and by using this equivalent plate with shear stiffness, you can then back calculate the stresses. You can then look at the buckling behavior, which is one of my favorite topics, but you can then look at the buckling behavior of this structure as you change the size of things. And you can also look at vibrations and more dynamic effects, because the dynamic effects will also be related to the shear stiffness. So for these big complicated structures that you don't know where these passageways are going to be made for either manholes or plumbing or electrical systems or other things, there's just too much detail that hasn't been decided at the conceptual stage, it is way easier to build up a simple hand calculation model or a very simplified FEM analysis where you can toggle or you can tweak the equivalent stiffness to approximate different designs. That's before you have all these other systems figured out and you're working in a large organization. You can come up with a very simplified result, have some initial answers to some big questions, which is overall stiffness, stress, vibration, buckling, and just overall configuration. And then when you have more systems information, you can update your solid models, you can update your real finite element model. And hopefully, if you do this right, you don't have to go through this iterative loop too many more times. Okay, but that's it for now, guys. I just thought I would share that. And this is a good overview. I'll probably have more to say about this later. And I'll talk to you later.